Now, let me move on to discussing the NDCQ, the non-degenerate constraint qualification, but this time for optimization problem with inequality constraint. Actually, the way to do it is very similar as before. We're going to form the Jacobian matrix. But the Jacobian matrix is formed by, well, the rows. The rows are given by just a gradient of binding constraint only. So we're going to look at which constraint is binding at that point and only consider those binding ones and form the Jacobian matrix. And then what is the NDCQ in this case? The NDCQ says that you want the rank of the Jacobian matrix to be exactly the number of binding constraint. Okay, so this is what I write down here. So for point P, to satisfy the NDCQ, we want the matrix formed by the gradient of the constraint function for just the binding constraint to have full rank, okay, to have full rank. And then we say that our optimization problem satisfies the NDCQ if every point from the constraint set satisfies the NDCQ. So it would be a lot easier if we look at a concrete example. Okay, let us look at example together. Check the NDCQ for the following optimization problem. We try to maximize a function. Well, when you check the NDCQ, the function itself, the objective function, is not very important. The most important thing are the constraint, okay? So what are the constraint in this case? The first one is x squared plus 2y squared less than or equal to 6. The other two are the non-negativity constraint, x greater than or equal to 0 and y greater than or equal to 0. The first thing we should do is to transform these two constraints into standard form. So you want to rewrite this as minus x less than or equal to 0 and minus y less than or equal to 0 to make sure that the inequality is pointing at the correct direction. Okay? So how do we analyze the NDCQ in this case? Because NDCQ only concerns the binding constraint, so let us define ourselves into three cases. Case 1. What if only one constraint is binding? Okay, only one constraint is binding. So only one of them is binding. For example, if only this one is binding, okay, let me say B, okay, it's binding. Then what is the corresponding Jacobian matrix? Then the Jacobian matrix equals to, well, is the gradient of the constraint function. So this is the constraint function. And then if you take the gradient, so for example, let me call this H1. And then the Jacobian matrix is given by the gradient of H1. So in this case, it will be 2x and 4y. And then for NDCQ to be correct, you want to make sure that this one has rank 1. But is it possible for this to have rank less than 1? Well, if this matrix has rank strictly less than 1, so rank 0, then what does it mean? It means that, well, the two entries has to be 0. That means that x equal y equals 0. But is that possible? Because if x and y are both 0, this constraint is not binding, okay? So this contradicts with the assumption that x squared plus 2y squared less than or equal to 6 is binding. Okay? That means that, oh well, this guy will never have rank 0, so this guy has always rank 1. Okay? So, the Jacobian matrix has rank 1. Okay, has rank 1. That means that NDCQ is satisfied. But what if this time is this constraint that is binding, okay? So, if minus x less than 0 is binding, then the Jacobian matrix equals to, well, in this case, you just take the gradient of minus x, so you get minus 1, 0. So, well, this guy obviously has rank 1. Okay, so okay. So NDCQ is okay. And then finally, if minus y equals less than or equal to 0 is binding, then the Jacobian matrix equals to 0 minus 1 instead. Then also this has rank 1. So again, NDCQ is okay. So this is how we analyze the first case when only one constraint is binding. Okay? And then the next case is, well, when you have exactly two constraints that's binding, when exactly only two constraints are binding, then the Jacobian matrix would be, okay, well, if it's this two that's binding, then the Jacobian matrix will be formed by the gradient of h1 and then also the gradient of this. So the Jacobian matrix will be 2x 4y minus 1, 0. Or if it is the first constraint and the last constraint that is binding, then the Jacobian matrix will be 2x 4y and then 0 minus 1. Or if it's the last two constraints that's binding, that's when x and y are both 0, then the Jacobian matrix are minus 1, 0 and 0 minus 1. And you want each of this matrix to have rank 2. Well, this is of rank 2, so it's okay. But how about this 2? Then you ask the same question. Is it possible that this have rank less than 2? Or is it possible that this row is a 0? It turns out it's impossible. So note. If 2x equals 4y equals 0, then x equals y equals 0, then the constraint x squared plus 2y squared less than or equal to 6 is not binding. Then this contradicts when we assumed this constraint is binding. So therefore this is impossible. So it turns out all of them has rank 2. So hence NDCQ is valid. Okay, so we don't have to worry about that. The final case, if all constraints are binding, so that means that all the three inequality becomes equality. So you have x squared plus 2y squared equals 6, x minus x equals 0, and also minus y equals 0. And obviously, this is impossible because if minus x equals 0 and minus y equals 0, that means that x and y are both 0. But then, well, obviously, it does not satisfy the first equality, so which is impossible. So the third case is actually impossible. Hence, by this analysis, we realize that in all possible cases, the NDCQ is satisfied. So hence, the NDCQ is satisfied for this optimization problem. The next theorem that I mentioned here is just to confirm that NDCQ is very important. It's actually as identical as before. That is, whenever NDCQ is satisfied, then the first order condition that we try to write down painfully will be enough to give you all the possible candidates for maximizers. Okay? So that means that once you have confirmed NDCQ is satisfied, you just need to solve the first order condition to hunt for the maximizer for the optimization problem.